Today we are going to deal with a very interesting topic under the oxidation of fatty acid. That topic is alpha oxidation. Alpha oxidation has not received much of attention till about 1946. Why it receives attention in 1946? Because Dr. Sigvard Refsum identifies that phytanic acid, so this molecule is getting accumulated in liver, in kidney as well as in brain. Now this is leading to neurological disorder, and he identifies this as an autosomal recessive neurological disorder. It is only then that phytanic acid getting attention. Now looking at the structure of phytanic acid, for example in 1960s, they identifies that this is a branched chain fatty acid. As you can see, there are number of methyl groups attached to this fatty acid. So if you look at this, this is a 16 carbon fatty acid. This fatty acid can also be called, this is, if you number the carbon atoms from here, 1, 2, 3, 3, 7, 11, 15. All these places there are methyl groups, so therefore tetramethyl hexadecanoic acid. 3, 7, 11, 15 tetramethyl hexadecanoic acid. Now why this molecule is getting attention is because this molecule cannot be oxidized through the normal beta oxidation process. We are aware that the normal beta oxidation takes place between, this is the alpha carbon atom, this is the beta carbon atom. It occurs between alpha and the beta carbon atom. The normal beta oxidation is not possible because of there is a branching at the beta carbon atom. So therefore it got a lot of attention in 1960s. Different scientists began looking at how to oxidize this branched chain fatty acid. A little bit about the occurrence of this fatty acid. This fatty acid is basically coming from ruminant animals because they will be consuming a lot of leaves that contains chlorophyll. When you look at the structure of chlorophyll, we know that it has got a long phytol tail. And this is the phytol tail. And this phytol tail get oxidized to become phytanic acid. So now we begin the discussion of the oxidation of phytanic acid starting from here. Oxidation of phytanic acid will take place in locations like peroxisomes. That is a major location where oxidation occurs, alpha oxidation occurs. It is also being reported in some organisms taking place in mitochondria as well as in endoplasmic reticulum. By and large, the major site of its oxidation is peroxisomes. How do we get phytanic acid in our body? When we consume non-vegetarian food that is rich in milk or butter or ghee or cheese, these are the sources of phytanic acid in our system. On a diet which is rich in protein or based on milk products, about 50 to 100 milligrams of phytanic acid can be absorbed by our body daily. Now we look at how do we go ahead with the oxidation of phytanic acid. So look at the structure of phytanic acid. As I have explained, this is a problem that is created because of the beta oxidation. So this is in the cytoplasm, what is happening. So this is the phytanic acid. In the first step is to activate the phytanic acid. From our beta oxidation sessions, we would have realized that this fatty acid can be activated by fatty acyl-CoA synthetase. Fatty acyl-CoA synthetase requires an ATP molecule that will be hydrolyzed to PPI plus AMP. So therefore, we will get phytoyl CoA. Phytoyl S-CoA. So phytoyl CoA is the end product at the end of activation. This reaction will occur in the cytoplasm. Once this reaction occurs, this molecule will be translocated using a transporter. It will be translocated to peroxisomes. In the rest of the reactions, we are going to see in peroxisome what will happen to this phytoyl S-CoA. What happens once it is in the peroxisome? So all these reactions are happening in the peroxisomes. Okay. In the peroxisome, the first step will be catalyzed by phytonoyl CoA hydroxylase enzyme. So this enzyme is elaborately studied, and this enzyme requires iron for activity. It requires an oxygen. It requires very specifically alpha ketoglutarate, and succinate will be removed from that. As a result of this hydroxylation reaction, we are going to have in the alpha carbon atom a hydroxyl group is inserted. No, once the hydroxyl group is inserted, this molecule becomes alpha hydroxy phytanoyl CoA. Alpha hydroxy phytanoyl CoA. Now, in the next step is alpha hydroxy phytanoyl CoA is cleaved. A kind of a decarboxylation reaction occurs that is catalyzed by a TPP, magnesium dependent enzyme, alpha hydroxy phytanoyl CoA lyase or oxidase. It will remove a formyl CoA. So the formyl CoA removed is this. This formyl CoA is removed, which will remove the coenzyme A. It becomes formic acid. Ultimately, formic acid will release the carbon dioxide, and that is how it will be degraded. So it is important to notice that formic acid to carbon dioxide ratio is about 9:1. So there is a greater tendency to remain as formic acid and not as carbon dioxide. So after removing one carbon atom, now we are left with a 15 carbon atom, and that 15 carbon atom compound is pristanyl. So it is an aldehyde that is formed. There are 15 carbon atom, 1, 2, 3 into 4s are 12 plus 2, 14 plus 15 carbon atom. Pristanyl is formed. What happens to pristanyl? Let us look at it. The next step in alpha oxidation is the pristanyl will be now converted to pristanic acid. So aldehyde is converted to its acidic form, and that is catalyzed by an NADP dependent enzyme plus H plus, and enzyme is pristanyl dehydrogenase. So this is the enzyme which will convert an aldehyde into the acidic form. Now once the pristanic acid is formed, it has to undergo beta oxidation. So we know that in order to carry out beta oxidation, this fatty acid must be activated. So there are long chain fatty acid synthetases, long chain fatty acyl CoA synthetases. And as we know, that requires a molecule of ATP. ATP will be cleaved to AMP plus PPI, and it will become an active form, that is pristanoyl S-CoA. So this is the structure of pristanoyl S-CoA, and this will have 15 carbon atom, 1, 2 and 12 plus 2, 14 plus 15 carbon atom. Now this will be able to undergo beta oxidation. how the beta oxidation carried out for a branched chain fatty acid. Our story does not end in the alpha oxidation. We have made pristanoyl-CoA. In order to have greater clarity on how the complete oxidation of pristanoyl-CoA occurs, I've drawn the entire 15 carbon atom. They are numbered by using green pen. You can identify them, 15 carbon atoms, and you can also identify where the methyl groups or the branching occurs. And let us see how the routine beta oxidation is being carried out in the peroxisome by using the regular enzymes of beta oxidation. We are aware that oxidation must occur after the second carbon atom. So in the first round of beta oxidation, this carbon-carbon bond is broken. If you break that carbon-carbon bond, we know that this is a 3-carbon coenzyme group. It's a 3-carbon product. We know that this is a 3-carbon product, and that is nothing but a propionyl-CoA. A propionyl S-CoA is released. And it is a routine beta oxidation. Therefore, this particular carbon number 3 will have a coenzyme A attached with the help of beta ketothiolase enzyme. So that will undergo next round of beta oxidation. Now remember, in the next round of beta oxidation, there is no branching. Therefore, this can be removed. A 2-carbon unit can be removed as an acetyl-CoA. That is the second round. But when it comes to the third round, so in the third round, it is once more, it is a 3-carbon unit, and this will be removed as a propionyl-CoA. Propionyl-CoA. Then you have a 2-carbon unit that will be removed as an acetyl-CoA, followed by you have another 3-carbon unit. This is a propionyl-CoA, and followed by another 2-carbon unit, that is an acetyl-CoA, which means after these many rounds of beta oxidation, you are left with a 4-carbon unit. This 4-carbon unit is isobutyryl-CoA. Therefore, if we have to write in the final summary of all that happens to this 15-carbon fatty acid is, you are getting one propionyl-CoA, second propionyl-CoA, and the third propionyl-CoA. So therefore, 3 propionyl-CoA plus acetyl-CoA, there is 1 acetyl-CoA, second acetyl-CoA, we'll write B, and the third acetyl-CoA. So propionyl-CoA plus 3 acetyl-CoA plus 1 isobutyryl-CoA. This is the final summary of the alpha oxidation of phytol or phytanic acid. So we get 3 acetyl-CoA, 3 propionyl-CoA, and isobutyryl-CoA. This isobutyryl-CoA will enter into TCA cycle by getting converted into succinyl-CoA, and that is how the complete degradation of isobutyryl-CoA will occur. So in this short video, what we have done, we have looked at the origin of phytanic acid, starting from the phytol tail of chlorophyll, and how that is converted to a form that can be oxidized in peroxisome and ultimately getting charged into phytanoyl-CoA, and then systematically by beta oxidation, by removing 3-carbon, 2-carbon, 3-carbon, 2-carbon, how it is completely degraded into a useful form for energy production through beta oxidation.